Okay, good afternoon. This is our second part of the lecture on interface advection methods. Okay, if you recall, in the previous lecture, I discussed about the geometrical mapping based method, and in that, I discussed about the out of cell explicit linear mapping. Okay, today we will discuss about onto cell implicit linear mapping. Okay, so we know already that our x position at time step n plus 1 will be equal to position at time step n plus u time x t at n plus 1. Okay, so in case of explicit scheme, if you refer the equation previously I discussed, what was here? It was x t n. Okay, in the previous lecture, whenever I wrote this equation, this u was x and this was calculated at time t n plus 1. Sorry, t n. Now I am calculating it at time t n plus 1. So here you can see the position is being calculated at time n plus 1, and for that whatever the velocity data I am using, that velocity data is also taken from time step n plus 1. So if it is being taken from time step n plus 1, what it means? What it means? The approach is implicit. Okay, so approach is implicit. And again, we have to do linear mapping. So what is the meaning of linear mapping? The meaning of linear mapping is the way we have represented velocity in terms of linear interpolation of the velocity values known at the endpoints. In the similar way, I have calculated the value of velocity where I minus 1 by 2 comma j and I plus 1 by 2 comma j are representing the values of velocity at the faces of the cell. Okay. Now, what is our next target? Whenever we calculate the new position, that we apply some transformation. Now whatever transformation we are applying, because we have to do this only along the one dimensional side, so I am applying transformation only along x-axis, and in this transformation y will be remaining as it is. In the y direction we will not be doing any translation, we are doing translation only in x direction. But earlier in the explicit scheme, it was becoming b of x plus some constant. Okay, now it is becoming a of x plus a times ui minus 1 by 2 comma j, where a is given as 1 divided by 1 minus ui plus 1 by 2 comma j plus ui minus 1 by 2 comma j. Okay, so this is the transformation. Now this transformation, whenever I have to apply geometrically, what will be happening? Okay, so here you can see this thin colored line is nothing but my, what is thin colored line? It is my original grid. Okay, and this big portion is actually representing the cell gamma x. What was gamma x in previous case? Gamma x was because of the stretching of the interface, what would be the larger area. Okay, so whenever I will be considering the compression type velocity, this type of velocity, because of this velocity some portion of this cell will be moving here and some portion of this cell will be moving here. So basically this rectangle area gamma x is decided in such a way so that it is including the portion, shaded portion of this, which has to be shifted to the invert cells. Okay, now on this gamma x, if I apply this transformation, ultimately it gets compressed to sigma, where sigma is the area of the cell, area of the reference area of the cell, which is just linearly mapping on the actual grid. Okay, so in this way we can transform gamma to epsilon by using this type of implicit method. The difference is in case of explicit mapping, after we have obtained the gamma, then we simply estimated this based on the velocity of the previous time step. But here, whenever we are transforming gamma to sigma, then we are using the velocities known at the next time level. Okay. So this way we will be able to calculate the value of sigma, and which is the total area, and inside this if I do the summation of D, E and F, then I will be getting overall area. Okay. So again, this scheme is still having some issues, and typically when onto cell implicit method is done on a two-dimensional grid. When we move it along x and y directions, in that scenario we do not get conservation of area and conservation of mass. So that's why this scheme independently will not be serving the purpose. And I also told you that explicit scheme also, whenever we extend for the multi-dimensional scenarios, then it also does not conserve the mass. So ultimately, in case of geometrical mapping, one more method is proposed, which is called as combined linear mapping. In case of combined linear mapping, what is done? Mapping sequence is, first we will be applying implicit transformations along x direction, then we will be applying explicit transformation along the y direction. If we choose this combination, ultimately we find that our area and mass is actually conserved. How this happens, let's try to understand. So typically when I will be applying the linear transformation using implicit mapping, by which factor my volume will be changing? My volume will be changing by factor A. All are clear with this point? And when I will be applying explicit mapping along y direction, by what factor my volume will be changing? Or for a 2D case, area will be changing. Area will be changing by factor B. Okay. So in total, if I have to find what is the total change in area, total change in area will be A into B. All of you agree to this point? Because implicit changes the area by this factor, explicit changes the area by this factor. So ultimately total area change will be multiplication of A into B. Okay. Now the overall algorithm is that first we need to reconstruct the interface at time step n. After that, we need to perform the advection along x-axis by using onto cell mapping. And we have to get some new value of volume fraction, but of course this value will not be at n plus 1. This will be considered as intermediate value of volume fraction. Now on this intermediate value, we will be again reconstructing the interface, and after this reconstruction, then we will be performing transformation in y direction using the explicit mapping, and corresponding to that, whatever volume fraction I will be getting, that will be my new volume fraction. Okay. So in this transformation process, if you see, gamma y is the area which is obtained by using transformation y, and this area was already obtained by using transformation x on gamma x. Okay. So in this case, we can say that the area gamma x is multiplied jointly by two factors A into B. All are clear with this point? So it is transformed by factor A into B. So if this is transformed by A into B, then if we calculate A into B, this comes out to be this equation. All are clear with this point? Now, if we have to ensure the conservation of mass, what should have happened? If this is my cell, whatever the velocity is at these points and velocity is in normal directions, their difference should be equal to 0. Then only my conservation of mass for incompressible flow will be ensured. All are clear with this point? Because all your areas are same, so ultimately in incompressible flow, if this equation is satisfied, so this equation is coming from the requirement of divergence free velocity field, because for incompressible flow divergence of V equal to 0. So divergence of V equal to 0 gives me this equation. And now you can see that in this equation ui plus 1 by 2 comma j minus u, or if I take the second term, yes, vi comma j plus 1 by 2 minus vi comma j minus 1 by 2 can be simply written in terms of minus of ui plus 1 by 2 comma j plus ui minus 1 by 2 comma j. So if this condition has to satisfy, then these two quantities will be becoming identical to this quantity with the plus sign over here. Okay. So ultimately the ratio of A into B is becoming equal to 1. Ratio of A into B is becoming equal to 1. So what it means, with whatever area we started, gamma x, ultimately gamma y we have obtained the same amount of area but at some new position. Is this one clear? So if we are starting with gamma x but we are getting new area gamma y, but this gamma y is actually after its advection, then ultimately overall area is actually conserved. So in this scenario, two-dimensional case, if I use the combined linear mapping, then we are finding that divergence free, and if we apply the divergence free velocity condition which is mandatory for the incompressible flow, then my conservation of mass will be established. Okay, whenever we will be using this approach, what we need to do, we need to first use the implicit interpolation along x direction and then explicit mapping along y direction, and immediately in the next step we have to swap this direction so that asymmetries because of preference of single direction are not actually enhanced. So to do that, we are just swapping it like txe into tyi. All are clear with this point? So in the next time step, we are swapping this like this. One important point you need to keep in mind, if I start my initial process, with this type of mapping, then the multiplication of A and B does not become equal to 1 even if we maintain the divergence free velocity condition. Okay. So whenever you are using combined linear mapping, you have to understand that only this combination has to be applied. If you deviate from this combination, then our system will not be working. Okay. So this is I will not discuss in very detail, but I will give you very brief idea about some other related advection methods. So here you can see this type of approach comes under the category of Lagrangian methods, where by knowing the velocity value at the end points we advect the entire interface, and where we determine the amount of reference phase on a fixed grid which is to be transferred to the next cell. That type of scheme is called as Eileen scheme. Okay. By taking the advantage of these two schemes, generally we solve the 1D advection equation for volume fraction, and when we solve the 1D advection equation for volume fraction, then we need to calculate the fluxes across the boundaries of the cell, which will be algebraically determining that how much amount of reference phase crosses the boundaries. And for understanding this, you can again refer to the previous lecture where I have shown you the advection of one-dimensional interface using the volume fraction field. And some of you, those who are interested in understanding of this extension of this method for multi-dimensional situations, you can refer it from your textbook, so I am not discussing all these methods. Now quickly we can see one more thing. Whenever we have actually whenever we have studied about the interface reconstruction methods, then what we did, we defined two important parameters. One was the error and second was order of convergence. So here also let us try to understand what is the test for reconstruction and advection methods. Okay, so how we are doing this? This is the amount of error which will be ij summation ij h square times cij t minus cij 0, where 0 is the initial volume fraction and cij t is the volume fraction corresponding to time t. Okay, and whenever we will be moving to time t, what we need to do? We need to perform multiple interface reconstructions and interface advections, then only we will be reaching to time step t. Okay, so test is simple. You have three different circles. There are three circles which are of different radius, and these circles are linearly translated along this path. So this is the path along which these circles are linearly translated. What should happen? If there is no gradient of velocity exists in this and only the complete circles are just translated along this line, so at any point of time, if I see the location of the circle, these should preserve their shape. Okay, so if these are able to preserve their shape, we can say that this process is nothing but simply the linear translation. If these are able to preserve their shape, we can say that our method is able to successfully advect the interfaces for what type of cases? Translation, linear translation based cases. Okay, and this is the typical grid structure which is used, and all the circles are actually fitted initially inside this grid circle. So if you do this, you will be finding this type of outcome. Okay, so here three different lines are there. First is the small dashed line. So small dashed line is corresponding to actual circle. Then you have one thick line which is represented in the form of these steps. Okay, so what are these steps? These steps are nothing but different plick lines which are constructed on the interface. So this black color is corresponding to the situation. This is corresponding to the situation when we are having actually probably the CFL number equal to 1, and then I have small dashed lines which over here are kind of overlapped, but here these dashed lines are appearing with separate boundaries. So dashed lines are representing CFL condition equal to 0.1. Okay, and first photograph is for grid count of 128 into 128 and second is for 32 into 32. So one point is clearly established that when I will be having coarser mesh, then shape of interface will be more distorted in comparison to the finer mesh. Is this point clear? Another important point is, you can see that in case of coarser mesh, when CFL number is maintained equal to 1, then your lines are more closer to the actual profile of the circle. But when CFL number is maintained 0.1, then your lines are actually deviating significantly from the actual circle. What could be the reason? Typically, if from the understanding of single phase flow CFD you see, always our attempt is that if we are maintaining the smaller value of CFL, we will be having more stable solution. But in this scenario, whenever you are going for the smaller CFL number, our solution is deviating much. What could be the reason? Can you tell me, can you guess what could be the reason? First point you need to understand is, if you have to start from t0 to some time t, then if CFL number is 1, then delta t will be large, and if CFL is 0.1, then delta T will be small. If your delta T is large, the number of time steps required to reach to the final time will be less. So it means less number of times you need to perform the reconstruction and advection of the interface. But if delta T is small, then the number of time steps needed to reach to the final point will be more. So if you have more number of points, what it means? It will take those who are getting late for lunch, maybe you have to go south, you can leave also. Okay. So what is the situation? Please tell me. You have to go for more number of time steps. Whenever you are going for more number of time steps, you need to perform reconstruction and interface advection more number of times. So if you are performing it more number of times, then whatever the small errors are accumulating in each time step, their magnitude will be more in case of the situation where you have taken more number of time steps to reach to the final point. Is this point clear? So that's why you have to keep this point in mind. Whenever we go with the interface advection, then sometimes maintaining CFL equal to 1 gives you proper interface reconstruction, whereas for the same final output, if you use the lesser time step, that may give you more amount of error. Okay. And one important point you need to keep in mind, when this solution is calculated, Elvira method is used for reconstruction of the interface in the intermediate time steps, and linear mapping methods are used for the interface reconstruction. Okay. And this you can see the amount of error associated for different type of grid cells. So for 40 into 40 the error is highest, and whenever I am decreasing the cell size, then amount of error is actually least. Moreover, you can see during the initial time error is more, and finally the error is actually kind of becoming stable. So from this data you can make comments on order of convergence. Okay. This is another situation. So we have done one test for linear translation. Second test is for testing the rotational flow. For testing the rotational flow, one box is taken, and inside this box velocity field is specified by using this particular method. And here I can calculate u as del psi by del x, and del psi by del y, and v as minus del psi by del x. So using this finite difference formulation, I can calculate the velocity field in each and every time. And you can understand that the psi is involving a cos function. So if it is involving cos function, from 0 to pi by 2 it will be 1, and from pi by 2 to pi it will be coming negative. So sometimes it will be positive and sometimes it will be negative. So here you can see that cos pi t is linked with capital T, where capital T is the period. Okay. So when t is small t by 2 or its odd multiple, corresponding to that I will be getting, say, clockwise rotation, and when t is multiple of t, then I will be getting, say, counterclockwise rotation. Is this one clear? So my rotation is keep on oscillating. Now in this oscillating rotating field, somewhere over here I have placed a circular fluid element. So what will happen to this circular fluid element? When the rotation is taking place like this, it will deform in the form of a long lamella at the period of t by 2. But when I will be in the next step, I will be again coming back to the original situation, then it should regain its shape to the original situation, if we are not considering any viscous dissipation in this scenario. All are clear with this point? So that is for corresponding to t equal to t. So here you can see the actual shape of the interface is represented by form line, and predicted shape of the interface is represented like this, and here you can see these are the dashed points, which shows how because of the errors in the interface reconstruction, we are having differences between actual interface and the reconstructed interface. Okay, and if you perform this process for large number of time steps, then you can see what will be the situation. Is this one clear? So typically, whatever methods we have studied, if we use these methods properly, then these will be able to reconstruct the interface properly. If say we are not using these properly, then we may have even errors in the interface reconstruction, and our interface will not be mimicking the actual scenario. Okay. Of course, after this, there are large number of advancements has also taken place in order to further improve all these methods, and whatever we see in recent softwares, there we have more advanced version of all these reconstruction as well as the advection methods. Okay, where even with the these are having more stability and more accuracy in comparison to some of the initial methods. Is this point clear? So probably I will stop with this point, and maybe in the next lecture we will quickly discuss about the estimation of surface tension force, because whenever we are considering the one fluid formulation, only two additional steps we need to do in addition to the single phase flow. One step was interface reconstruction and advection, that we have done, and second part is in the momentum equation there is a surface tension force. We have to also see that how we can discretize the surface tension part in order to numerically calculate its value. So that I will take up in the next class, and after that in the remaining lectures we will briefly discuss about the phase change fluids, okay, particularly the boiling and condensation phenomena.